Hey everyone, sorry about having to back out all of a sudden and back in. Hopefully it's working now. Okay, I got more people than I had last time already, so that's good. Now hopefully this will continue recording and we won't have any problems, but we'll see how that goes. Here it is. Says I have only 490 gigabytes left. It should be more than enough for this video anyways. Yeah, please go ahead and everybody chat me your first and last name for attendance. That would be super helpful. Looks like we got enough people here for right now, so I'm going to go ahead and get started. I asked the people that came in earlier, so I'm going to ask you again. Does anybody have any questions you might need answered? I did already announce that because of me missing a couple of days due to sickness, I will be I might have to push the date of the first test back. I might not. I don't know. I've got to look at that date, and I haven't looked at the syllabus that closely recently. But I did manage to clean up a lot of stuff. Hopefully, y'all saw that in the messages I sent you. I cleaned up the helpful documents and links pages. Made sure I cleaned up my syllabuses. They had some errant dates, and they also had some incomplete explanations of my office hours. So all that's been checked. Uh, I've also shown you equations that you're allowed to use for the tests and stuff like that. Yes, Jennifer, you have a question?
I have a couple questions. Actually, one, the practice tests are still not open?
They should be open now. Is it you literally just tried it?
No, but it was about 10 minutes ago.
Oh wow, that really should be
Yeah, it
open.
still says
They're
past due
set
date.
till July 31st.
Okay, that's another thing. So I must not have paid attention to the due dates, which I don't know why it had the dates on it anyways, but I can fix that real quick. I actually had to fix it because a lot of them didn't have any questions in them, and some of them just had a couple questions. Ah, yeah, I see the date. Of course, yeah, that's wrong. So evidently I went through all that time correcting all that for no reason because I had a friggin' set date was wrong. Now that date, I've now opened test one, practice test one, and it does not have a due date. Uh, Normally that will disappear on the day of the first test. So if the first test is, of course, the first online test, whenever that's due, it'll disappear. That means you don't get another chance to do it. So keep that in mind. Now I'm going to do the same thing about practice test, which it says practice test 3. I would normally call that practice test 2. I'm going to go ahead and write it as practice test 2 now. And that also had an erroneous date. So I'm clearing that and clearing that, and I'm going to double check, make sure it has the right number of questions. Yes, it seems to be behaving okay. So the practice test PT01 and practice test PT02 are now available. I have all the questions in it. I double check that. You have another question, Jennifer?
You have the online test is set for the 16th, actually, which is Monday.
Gotcha. Yeah, that's a little early, ain't it?
And so that one is the one that we can take at home, right? Or is
Yes.
that the one we need to schedule?
No, as far as I know, that one's supposed to be the face-to-face, or excuse me, the online test. I think I chose not to make a first face-to-face test until you covered chapters 1 through 4.
Okay, so there will be face-to-face tests with the online tests and midterms and stuff? Or
Yes. Well, I say they're face-to-face, like we have a way where you can test them at the testing center on any of the campuses. But if you can't
that's what I
actually
wanted.
make it to a campus, we have other ways of doing it.
No, I was going to go to the campus, but I was just trying to figure out if the dates were set so I could schedule my tests with
Oh,
the
gotcha.
campus and my babysitters and everything, or
Gotcha. If you want to use those dates, I can make sure they happen on those dates as listed in the syllabus. And you can go ahead and book them and I'll honor them. That's not a big deal to me. But if you want to just wait, I'm looking at it right now. I'm pulling open the
Well,
syllabus
it's
to
about the
see.
coursework. I have to be able to, read the chapter before I can take the test. So
Exactly. You don't want to jump into it without being ready. Yeah. So it says, my first online test is September 16th. And yeah, that's just an online test. And that's due this coming Monday. I'm probably just going to push that back to the 23rd just because of the problems I've had. But that means I might have another one the very following weekend. That's test
it's
two. And then we don't have a midterm until October 16th. That's a face-to-face test. So October
that's face
16th
to face.
and November 13th is another one. And then the last one, that's the second midterm. I thought I'd put three in plus.
The second midterm is the 13th of November.
Yes, ma'am. That's what it says. I thought I had put in a third one in there, but I don't see it right now.
I
So
didn't see it.
yeah, I might have to add another one later. And my instincts tell me it would probably be we don't have class on the 27th. I've clearly put that in December 4th. I think that was supposed to be where it was, December 4th. Should be third midterm, and then December 27th was supposed to be no class. So that's probably what we're
So
leaning
those
towards.
tests, those face to face tests, you're not going to have those in the lab portion then, right?
That's what we do in the summer. We can't do that in the regular semester unless the lab teacher doesn't necessarily have a lab for that week. But every week is spoken for, so we're gonna have to have it where you take it probably during some 7 day interval at a testing center, and then if you're somewhere where you can't get to one of our testing centers, then we'll find another way to work it out for you. There are ways, for instance, you can take it proctored online. Uh, there's services that'll pay for that. There's free service that's Respondus Lockdown browser with the Respondus monitor. And then that I just ask you to have another mirror with you, and that would be about it.
No, I can't take it at home.
You don't want to take it home, or
I
you
have
can't
too
take
many
it.
kids. I have kids running around.
Oh yeah, they make life very interesting. But yeah, you can certainly do
Um,
any of the facilities on campus, on any of the campuses. And
I don't
sometimes
want to
local librarians will help you too.
take up too much time. I do one more question. As
Yeah.
far as what we can bring, you have posted those now. I believe it's 5 sheets of paper.
Yeah, I have the equation sheets that are on there, and you're the 242, 241 class. So it's just the 241 equation sheets plus the front covers. You don't have to bring them because when I make them, they're at the bottom of your test. So
Can I
and you'll
bring
see
them?
that on your practice
It's
test too.
easier for me if I have it on the sheet of paper. Can I bring it on the sheet of paper?
Yeah, just be advised, they are told to take photographs of it in case you doctored it or anything. So don't doctor it. Don't even write things
That
on
was my other question. Can I write the equations in my own handwriting?
No, we have to. Well, I wouldn't generally have a problem with that, but generally, when I let people do that, then they change things and write sentences that describe what things are and that kind of stuff.
Yeah, in
So,
my calculus class, they recommended it because it helps you connect with the information better.
yeah, I definitely highly recommend writing it down as many times as possible. But I
Yeah.
suspect you'll get that if you're solving
It's like when
problems,
you're
unless you're
nervous for
solving
the
them.
test, it helps you.
Yeah,
But it's cool. As long as I can bring the paper that I can print out,
yeah, that's not a problem. And
I'm
it
good
is
to go.
kind of
All
a
right.
pain scrolling up and down and that. I totally get it.
Yeah, I had trouble with that before.
In fact, I could possibly the testing centers might actually print the stuff out for you if need be. I'm not sure. Dylan, you had a question too?
Yeah, I was gonna see if you would be able to meet after this class. I had some other questions and some of the homework stuff I wanted to go through with you.
Yeah, yeah, and that's why I sent that email out to everybody just in case anybody didn't realize I would be online tonight to teach. So yeah, that's definitely an office hour for you guys as well as for everybody else.
Okay, and I did have one question on the practice quizzes. Is there any way
Mhm.
you can make it so it shows the correct answer if you got it wrong? Because now it just shows you got it wrong, and then you try and take it
Yeah,
again, and you get a random set of questions, so you never know where you went wrong.
Right. You can actually look at all past instances of you taking it. So that's helpful, at least with the practice test. But generally I've decided no, not to give you the answers, but I will, any particular problem you don't know how to do, you can come to me on a one-on-one basis, through Zoom or office hour or something like that and get help, and I'll show you exactly how to do it and make sure you find the right answer. I just don't put them en masse like that because I discovered that they just come back and fill in other people's answer sheets when they're taking tests.
Okay.
So yeah, it's just a practice that there's a limited number of physical problems we can actually solve without having to write computer code. So we try to protect those as much as possible. Then places like Chegg come along. I will tell you, Chegg has a lot of those answers, and they're almost always right. So if you
Yeah, I
look
noticed
for 'em.
that. I noticed that when I would search them, but when I have downtime at work, I've been working on them, but all those sites are blocked, so you can't log into them. So I can't see the answers anyway.
Yeah, gotcha. Yeah, if you pay for the, I mean, they'll charge you, and when you charge for it and you actually pay for it, they'll give you extra all the solutions and all that good stuff. But again, they're not all correct. They're from solutions manuals. They're mostly correct though. So you can certainly do that, and it might be worth your time to buy it. I would say no, it's better for you to solve it again and or solve it. Look and see if you made any careless mistakes. If you didn't, then ask me about it, or ask another person who did get it right. That's all fair. Okay, so
Okay.
feel free to ask me, and you can, definitely have a photograph of the problem that you did, as well as the multiple choice answers, if it is multiple choice, so I can not only tell you which one's the right answer, which one's the best answer. So definitely do that.
Okay. Sounds good.
Okay. Yeah, that is an ongoing thing, everybody. Jennifer, I got all yours right.
Yeah, you did. Thank you.
No problem. Anybody else have any questions?
Hey, Professor, I just had a
Yes.
question. What's the main difference between the practice quizzes and the practice tests?
Okay, so the chapter practice, what I call chapter practice quizzes, they are ones that I can see how often you take it, but I can't see any kind of grades you made on it, and they're strictly for that chapter. So like when
Okay.
you look at chapter practice, chapter one, that's just a quiz. It's normally one concept question and three workout problems where you have to solve algebraically and stuff like that. And there were 3 points each for the problem solving ones, and then 1 point for the other ones. So that gives you a net of 10 points. And you can take it over and over again. It's really for fine tuning. Like when you take the practice test and you see, well, crap, I did really well on chapter 18, but chapter 17, I just don't get. Well, then you can go back and take, I know that's not one of your chapters, but you can go back and take just a chapter test on 17 to focus on it.
Okay, cool. Thanks.
Right. And that's, when you look at these banks, there's usually on the order of 100 questions at least per practice test. So that's giving you access to them per chapter, which is really kind too. That's another way you could, for instance, as Dylan was asking, find out what the right answer is, because chances are it's going to pop up there somehow too.
Oh,
But
like sometimes the questions are shared.
yeah,
Okay.
they're all from the same banks.
Okay, just chapter
Yeah.
specific for the
So just
quizzes. Okay.
please don't propagate it. Please don't take screenshots and put them on the internet. That, like I said, it's just
Yeah, I
it
gotcha.
kills us as
Yeah.
physics instructors. Just
Yeah, I
find problems
understand.
that we can assign.
Got it.
Thank you,
Sounds
guys.
good.
All right. Well, I've got some problems worked for you. What you'll see is a large part of the work that you're going to do in chapter two, which is the kinematic equations, is really just learning how to apply those kinematic equations. So in my notes today, I started off writing down what are the 9 kinematic equations that I've already derived. I've written some definitions, so they might be helpful notes for you to keep as well. But the main thing is, once we have those, we need to know how to apply them. A good part of learning physics, especially your first time taking physics, is about learning what are the equations the instructor gave me in a given chapter. What are all the symbols in those equations? And, of course, that means what do they mean and what are their units, because the units that they're in is often the only tell for you on figuring out what the quantity is. And then figuring out which equations you should use in which scenarios. So a large part of it is just identifying variables and noticing what's been implied in a question. Like, for instance, if I say an object is dropped, above planet Earth where the air resistance is negligible. From that, you should be able to get not only that it's on planet Earth, but that the acceleration is downward and is 9.80 meters per second every second, and that the initial velocity was 0 because I used the phrase drop. So we had a lot of information that way. We don't necessarily hide it. We're just trying to speak in everyday language and want you to learn how to translate that everyday language, like an object was dropped, to mean, oh, the initial velocity is 0. And the fact that it was over the planet Earth tells us we know exactly what the acceleration is. And the fact that there's no air resistance means I don't have to worry about air resistance. So just keep an eye on that. Let's go ahead and get started. I'm going to start by sharing my screen in principle. So let's see if I can do that. Ow, ow. They've hidden the share screen under 3 tabs now. It's driving me crazy. I think I say this every class, so I'm also going senile, evidently. All right. There we go. So I've taken the time. I apologize for writing in cursive. I will read it to you, and then you'll have the video version of it, so you can still have it read to you if you're not that comfortable with cursive. But here it is. Displacement, the change in position of an object. Later, we'll see it as a vector that points from the object's initial position to its final position. So what we're going here for is we're hinting at the existence of this concept of a vector, which is correctly described in Despicable Me by the villain vector. It's an object that has direction and magnitude. So you can imagine that just an arrow is a very good representation of a vector. So you might picture the displacement as a vector that points. In other words, the flat end of the arrow sits right where the object was initially, and the head end of the arrow sits right where the object was at the final time. That is the displacement vector. In one dimension, we normally just call that delta x, which means x final minus x initial. That's a big rule too in physics and chemistry. When you see that capital delta, which is what looks like an equilateral triangle with the one side down instead of the point being down, that is a delta. And that always means final minus initial of whatever comes after it. So if it said, as you can see here, if it said delta r, that would be r final minus r initial. If we're doing it in multiple dimensions instead of just one dimension, then we actually have to break it up and call it 2-dimension or 3-dimensional motion and use the vector symbols. So a more typical result is the displacement is delta r with an arrow over it, or sometimes we will use delta x, even though it's x makes you think of the x coordinate or the x-axis, and it's supposed to be in general a position vector. There are a lot of books that use x for a position vector instead of r. Caution, the displacement is not necessarily the total distance traveled. You'll see that comes into play when we talk about average speed versus average distance. I'm going to give you one of those types of examples today, or a couple types of examples today. Average speed is distance traveled by time divided by time elapsed. That's what I call equation 1, and I went ahead and assigned it symbols. S bar equals d over t. Okay. Average velocity is the displacement divided by time elapsed. So you actually have to figure out exactly how much it's moved from its position in total. In other words, an object can walk from the 1 meter mark to the 1,000-meter mark and then come back to the 2-meter mark. And if you're studying it between that first part and the end, then the displacement is only 1 meter long because it went from the 1 meter to the 2 meter, even though it went way out to 1,000 and came back. Okay, so that's something to keep in mind regarding average velocity. When we do deal with vectors, by the way, sometimes they'll have negatives associated with them or negative components associated with them. That's just an indicator that it's pointing in the direction opposite of what you called positive. Instantaneous velocity. Oh, I did say average velocity. Notice we put a bar over it. I'll tell you that sometimes I'll put it in greater than, less than symbols too. That's another symbol you can use for a mean or an average. But V bar is equal to delta x over delta t. The instantaneous velocity just has to be argued as the average velocity, but you let the time interval get so small that the velocity doesn't appreciably change, or the position doesn't change too terribly much in that such a small time interval. So you end up getting the velocity at that particular time. So if you shrink, for instance, the delta t down to on the order of 100th of a second, most humans don't have 100th of a second reflexes. Some cats do. If you've seen videos of cats kicking the crap out of snakes, for instance, that'd be how they do that. But humans generally don't have that good of reflexes. So if you actually just brought it down to 0.01 seconds, there's a good chance that the human's not going to be automatically changing their speed in between the first part and the last part. So you're probably going to get an average that stays fairly constant over that whole area. But the main thing is by taking the limit as delta t approaches 0, you get a better estimate, and therefore you get what we call the derivative. Okay. So the velocity is the derivative with respect to of x with respect to time. Acceleration, instantaneous acceleration, in other words, is the derivative of velocity with respect to time. That's just a fact that you should now know. It does say average acceleration is delta v over delta t, and notice we put a bar on the other side. Again, that bar over top means average. It did say constant and negative acceleration does not necessarily imply an object is slowing down. Okay, don't get caught by that error. Just because an acceleration is negative, that does not mean it's slowing down. For instance, a car could be going 1 meter per second in the left direction, and then later be going 12 meters per second in the left direction. And maybe it only took 3 seconds, in which case the average acceleration would be -11 minus -1, which would be 12. Divide that by 3, and you get 4 meters per second. Negative 4 meters per second. And clearly the object was speeding up. Okay, so that's another caution for you to take into account. The instantaneous acceleration is defined just like the instantaneous velocity. You're still taking the limit as delta t approaches 0, but it's of delta v over delta t instead of just delta x over delta t. Now, you will recognize that from Calc 1 to be dv dt, and I'll just remind you that's also d2x over dt squared. So one of the equations that you probably know of physics, there's 2 of them that people know. One is E equals
MC squared.
Yep, and the other one's F equals, y'all might know this one, it's a little less known.
Mass times acceleration.
Yeah, exactly. F equals ma. Now I'll end up writing that differently. I'll use a sigma symbol before the F, but the A is literally a second order derivative. So in principle, even solving Newton's second law is a solution of a differential equation. So just letting you know that based on the derivative being the acceleration being the second derivative of space with respect to time. Now, if you go on with the assumption that A is a constant, then you can find 3 more equations. One of these equations is V bar is equal to V1 plus V2 over 2. That you can't just add 2 velocities and divide it by 2 to get an average velocity unless the acceleration is a constant. So that's another equation you can use. That's an equation you have to use in our 201, 202 sequence because they're not allowed to use calculus and don't know calculus. So that's the way we get around doing a lot of the derivations is by using that little nugget. You'll see equation 7 is the one I got from taking the integral twice. X equals 1/2 AT squared plus V0t plus X0. And then if I solve equation 4, if I solve that for time, you'll get time is equal to V final minus V initial over acceleration. You can then plug that in 7, and that will eliminate time, and you'll get equation 8, which is V squared is equal to V0 squared plus 2a parenthesis x minus x0. Okay, so those are all your equations and all the symbols you need to know. I hope that was a good recap for you. Now we just want to solve some problems, and you guys just speak right out if you have any questions. You can raise your hand if you want, but you're welcome to just speak out. If you get too rowdy or something, I'll ask you to dial it down, but that's never really happened, so we'll be good.
Professor, what did you say about which of those weren't supposed to use calculus on?
You can use calculus on all of them, but that equation 6 is what we use if we're trying to do the derivations without calculus.
Oh, okay.
So that equation 6, and I don't even remember if your book offers it or not. I can't recall. I just remembered off the top of my head because it sometimes can help you solve simple problems.
Okay, cool.
All right. Okay, so here's example 1. During a 5-second time interval, a runner goes from x0 equals 50.0 meters to x final equals 30.0 meters. What is the runner's average velocity? So notice I've given you x0 and x final. Those are the final position, x final, x sub f, and the initial position, x sub 0. Part of that was me reminding you what the sub 0 means and what the sub f means. Okay. But what I'm trying to do is use the definition of average velocity, and average velocity is delta x over delta t, which equals x final minus x initial over, we just normally call it time because we hardly ever say t0 is anything other than 0. So if you said t final minus t initial, it'd just be t final minus 0. So that's why we often just say t instead of delta t. With that in mind, we can go ahead and plug that in. We know that the final position is 30 meters minus the initial position is 50.0 meters. You can also see that I took the time to make sure it was unambiguous that these numbers had 3 sig figs. I try to do that in all my examples, and even the book examples that I borrow, I just make it change so that it has a clear number of sig figs. And this, in fact, took a time of 5.00 seconds. So the thing that mostly trips people up on sig fig stuff is when you do subtraction. There's always a chance that you could really horribly reduce the number of sig figs you have when you do subtraction. Like if I had 50.0 or if I had 30.0 minus just plain 50, technically just plain 50 has 1 sig fig. So the answer would be negative 20, which is right, but now you only have 1 sig fig. So that's a really bad thing. In this case, we got 30 minus 50 is negative 20.0 meters. And then I'm going to divide that by 5.00 seconds. So now I have 3 sig figs divided by 3 sig figs. And that, of course, gives us 3 sig figs. So I get negative, oops. Okay, don't know how that happened. So I get negative, dang it, 4.00 meters per second. And you can see in this case, if someone asked you the magnitude of the average velocity, you'd say 4 meters per second. There's no such thing as a negative magnitude when we talk about vectors, okay? There's no such thing as a negative magnitude. Now, when we get into quantum mechanics, all bets are off, but generally speaking, all vectors are supposed to have positive magnitudes. Write that down somewhere really big, because when we ask for a magnitude, we do not want a negative number, okay? But what it does do is tells you that this velocity is not like speed. This velocity is a vector quantity. It tells us not only how fast it's moving, but that it's moving in the negative x direction, which is the direction that goes from 50 to 30, not from 30 to 50. Okay. Any questions on that one? So yeah, that's pretty straightforward, right? If a car averages 20 kilometers per hour during a 3.25 hour interval, how far could the car have gone? Okay, so that's another one. In this case, we're talking about averaging. You could really go with average speed or average velocity in here. I didn't actually specify it. I'm going to use average velocity, or excuse me, average speed. And we know the average speed is distance traveled divided by time taken. But in this case, we're asking how far could it have gone? So I'm actually solving for D. So if I solve that for D, then I get D is equal to S bar times T. And that actually is a true equation, whether it be S bar, the average speed times time, or V bar, the average velocity times time. You can actually use that all the time. It works just fine because it is an average velocity if the average velocity is taken properly. Notice also that I'm solving this algebraically before I put the numbers in. Again, this is sort of what you should be aiming to try to do, but don't feel horrible if you finish the 2-semester sequence of this course and you're still not doing it that way. A lot of people don't, okay? It just helps you a lot. I had a good friend who's a very competent and awesome engineer, structural engineer. He couldn't, at least at the time where I had to help him, he couldn't work out algebraic problems algebraically, but he's a wonderful engineer and, designed, uh, waterfront hotels and stuff like that. So it doesn't mean you're bad or anything like that. It just means you're a little limited on some of the tricks you can do and some of the things you can do to analyze the problem. So do try to solve it algebraically and then put the numbers in. It also makes it easier for your sig fig stuff. So in this case, I'm going to say D is equal to the average speed, which we said was 20.0 kilometers per hour, times time, which luckily I gave it to you in hours. Notice if I'd given you minutes, you'd either have to convert the kilometers per hour to kilometers per minute, or you'd have to convert the time from minutes to hours. You have to have some kind of matching time unit when you're dealing with things like this so that the units that you don't need, i.e. the time units, can disappear. Of course, when we multiply 3 times 20, we get 60. When we multiply 20 times 0.25, we get 5. So this should be 65.0 kilometers. And notice that is 3 sig figs multiplied by 3 sig figs, so you get 3 sig figs. Any question on that one? Pretty straightforward, right? If a car travels at a constant speed of 70 kilometers per hour, how long will it take for the car to travel 210 kilometers? So this is another instance where you can use an equation and solve it algebraically first. But the main thing is I want you to realize there's a process you can go through. If you have the average speed, you can find the time or the distance. If you have the average distance, you can find the velocity or the average time. If you have the time taken, you can find the velocity or the average distance, but you got to have two of them. So in this case, the constant speed is the same thing as the constant velocity. So I'm just going to use it like this. I'm going to say S bar is equal to D over T. Whoa, evidently S bar is going to be D over D. All right, so S bar is equal to D over T. And what I want to know is how long, or T. So T is going to be equal to the distance traveled divided by the average velocity. So in that first case, I'm talking about 210.0 kilometers. If I just written 210, that would have clearly 2 sig figs, or your book. Remember this too, by the way. When you take an online test, I'm using the textbook's questions, and according to the author, he would say the number 210, just 210, he would say that has an ambiguous number of sig figs. In my lab, and probably in your lab too, we use a rule that if the decimal place is present and you wrote 210 without the decimal place, that would have 2 sig figs. If you wrote 210 decimal, then that would have 3 sig figs. And if you wrote 210 decimal 0, that would have 4 sig figs. Okay. But keep in mind that that's what the author says, because there will occasionally be an extra or a homework / test problem that asks you, like, how many sig figs does 5,000 have? All right, so we got 210 kilometers. I got to divide that by the average speed, which is 70.0 kilometers per hour. Notice again, the kilometers matches with the kilometers per hour. You need the units to match when you're using this equation. So since the kilometers do match, the kilometers will cancel each other out, and it'll come out in units of hours, because the hour is in the denominator of the denominator, and you know that when you divide by a fraction, you end up multiplying by the fraction's reciprocal. So it becomes hours over kilometers times kilometers, and you see how the kilometers cancel out when you do it that way. Okay, so when I divide 210 by 70, I actually get 3.00 hours. And that is the correct answer for that part. And I said, what about traveling 50 kilometers? This case I did specifically so you'd see it's not always obvious. I'm trying to use really obvious numbers so I don't have to use a calculator and y'all can immediately see what happened. But when it's a smaller distance than the velocity is, at least in terms of kilometers, it gets a little more confusing. So I want to make sure y'all are aware of that and how to deal with it. So in this case, I'm going to again say that T, oops. I'm going to again say that T is equal to distance traveled divided by the average speed. In this case, I'm going to say 50.0 kilometers is divided by 70.0 kilometers per hour. Again, multiplying by the reciprocal of kilometers per hour is hours per kilometer, and you see that the kilometers cancel out, and you get 5 divided by 7. I know that 1/7 is 0.1428 roughly, so 5/7 would be 5 times that much. That'd be 50, 70, 71 point 5, 71.5, something like that. Let's check. At 0.715 is what I was shooting for, by the way. So 50 divided by 70 is 0.7142. Equals 0.7143. And I carried one extra sig fig, which is always good practice. But that's basically what it is in hours. I suspect that most people don't know what 0.71 hours is, so I'm definitely going to convert that to minutes. And that's not something you have to do unless I explicitly tell you, but I would say that's good practice either way. So let's go ahead and convert that. What I'm going to do is I'm going to multiply it by 60 minutes divided by 1 hour. And then you'd see that the hour cancels out with the hour on top, and you get 60 times 0.71428. And that gives me 42.9 miles, or excuse me, minutes. Okay. So in everyday life, I sort of do this stuff a lot. I do a lot of calculating my average speed, especially when I'm on long trips, mainly because, well, I'm ADD. So get on the road and driving is just not stimulating enough for me. So I do math in my head by dividing the odometer readings by my watch readings and then estimating how long it's going to be to get to the next exit or the next bathroom for the kids or the dogs or whatever and stuff like that. So I would say that's a really good practice to keep one, to stave off Alzheimer's, two, to keep your arithmetic skills up to snuff, and three, just to keep yourself, avoiding dementia and all that good stuff and learning physics. So anybody have any questions on that example?
Professor, for that first example, did you say it was supposed to be always positive since it was a vector?
Yes. So what I gave you was the vector.
Yeah.
If I asked you the magnitude of that average velocity, I would have had to report 4.00 meters per second.
Oh, okay.
But
specifically the magnitude. Okay.
Exactly. In one dimension, the negative is the direction. And if it was a positive, that's the direction too. When if you're asked the magnitude, though, you should say 4.00 meters per second as a positive. Good question. If you paid attention to that. All right. Now this one, it says a car travels at a constant 80 kilometers per hour for a distance of 240 kilometers and then proceeds at a constant speed of 120 kilometers per hour for 2 hours. What is the car's average speed? Now, I've seen a lot of people try to solve this, and I want you to know you're only allowed to use the formulas that we give you, the equations that we give you, because they're definitions. For instance, you can't just say, oh, well, this looks like the person traveled 80 kilometers per hour for 240 kilometers, but traveled at 120 kilometers per hour for 240. So I'm just going to average 80 and 120. That's not the definition. That's not the definition of average velocity. The definition of average velocity is V bar is equal to the displacement divided by the time taken. So we know what the displacement is for the first part of the trip. So first part, what we have is delta x is equal to 240.0 kilometers. But in order for us to calculate the average speed, we're going to need the time it took to. And I think you can see from that V bar is equal to delta x over delta t gives me that delta t is equal to delta x over V bar. And of course, that gives you 240.0 kilometers divided by 80.0 kilometers per hour, which gives me 3.00 hours. Okay, so that's just the first part. The second part, so the second part of the motion is the car traveling at 120 kilometers per hour for 2 hours. So we also need the distance here. So distance delta x is going to be equal to V bar times delta t. And of course, that delta x is equal to 120.0 kilometers per hour times the amount of time, which is 2.00 hours, which gives me 240.0 kilometers. But now I only have 3 sig figs. Okay. So that's something we definitely need, but we also know that delta t for this part was equal to 2.00 hours. So those are the two parts we need. I can now say that the average velocity is delta x over delta t. And of course, that's 240.0 kilometers plus 240.0 kilometers. Notice how I underline that 0 there. That second 240 kilometers is really only good to 3 sig figs. And now I got to divide it by 3.00 hours plus 2.00 hours. And you can see that is 480.0 kilometers divided by 5.00 hours. And 480 divided by 5, that's almost 100, but it's 20 less, and 20 divided by 5 would be 4, so that should be what, 94? I'm going to say 480 divided by 5. Okay, my calculator did some weird stuff right there. I got I said 96, 94, not 96. I meant 96 kilometers per hour. Okay. So see how we did that? We had to use what we know of as the definition of average velocity, which is the displacement divided by the time taken. And that required a little bit of computing for us to do it. Anybody have any questions on that? So keep that in mind. That's one of the ways we can we're not trying to trick you. We're trying to discern whether or not you know exactly the definitions of average speed and average velocity. The major differences, and I said this in class, I know I probably said it to you guys as well, but it's a common misconception that speed is the magnitude of velocity. But at the same time, that's almost always true. So if you take the speed, the magnitude of a velocity vector, that is essentially defined to be the speed in most cases. But if you start talking about average velocity and you imagine a kid, playing t-ball, he hits the ball, steps on home plate, runs to first, steps on that, steps on second, steps on third, steps back at home plate in the exact same spot. at that point, if you're wanting to calculate his average velocity when he stepped home, the displacement was literally zero. So the average velocity would be zero, but the speed would be that, 60 times 4 divided by the time taken. So there only needs to be one case of falseness for such a question to be a false when you're answered a true false question, like the speed of or excuse me, the magnitude of velocity of speed. That's false because you can find at least one example where it's not. Does that make sense? All right, so that was another problem. That one pretty straightforward, but I gave myself a lot of room just to make sure. And then I followed it up with giving myself almost no room for this ginormous problem. So it says the position of an object is x of t equals 4.00 t cubed plus 2.00 t minus 3.00. And I'm going back to my roots here by reminding you guys that you should always be thinking about the units and dimensions of numbers when you're dealing with them. So me writing 4t cubed and 2t should, get you a little nervous. It should immediately make you think, what's the units of that? What's the units of that? I need to know the units of that. So in part A, I asked, what must be the units of 4.00? Anybody want to suggest an answer for that?
Would it be like some form of volume?
Very much like that. Because you're thinking of the t cubed would be meters
Yeah.
cubed or something, right? Now what it is remember the unit of x, which is on the left-hand side, that has to be meters. So I've got to have a meter in the 4 as well, and the meter needs to be in the numerator. But then I've got to multiply it by seconds times seconds times seconds, and I don't want any seconds left, so I've got to make sure I cancel those out. So you might be able to reason that that is meters per second cubed. And that's the answer for that first one. Everybody understand how I did that?
Yeah.
Okay. So 2.00, maybe y'all can figure that one out before I get to writing it down. And then the 3.00. So the 2.00, again, I have to spit out meters and I have to multiply by seconds. So that's going to have to be meters per second. And the 3.00 has to spit out meters, but it doesn't have to multiply by anything. So the meter is just fine. Does everybody agree with those answers?
Yeah.
And that's true. I mean, that's the kind of thing that I've done in major engineering projects and major big homework problems. And I keep track of those units throughout. And that's a good check for me to make sure I haven't made any careless mistakes, because if the units come out wrong in the end and I checked it all the way through, then I know I've done something horribly wrong. So keep that in mind. All right, let's move on to part B. So it says part B, what is the positions at t equals 0.125 seconds and at 3.00 seconds? I didn't say explicitly the t equals, or I said it, but I didn't write it down. But I just wanted to make sure y'all realize when it says seconds, that's the time. So I'm going to say x of 0.125 seconds is equal to 4.00 meters per second cubed times 0.125 seconds cubed plus 2.00 meters per second times 0.125 seconds minus 3.00 meters. Notice I put all the units in there. So I'm going to say 4 times 0.125, and I'm going to raise that to the third power. And that gives me, I'm going to go ahead and write up in 3 different terms just to help you guys see it a little better. Now I'm only supposed to have 3 sig figs, so but I put more of them on there just so you'd see where it come up. Now I'm going to do 2 times 0.125. I suspect you all know that's 0.25. Oh, and I shouldn't put a plus there. I should actually put a minus there. So I'm going to do 0.0078125 plus 0.25 minus 3, and that gives me negative 2.742 meters. That's x of 1/8 of a second. Just it saves me room to write that as a fraction because I know that 0.125 is 1/8. I can do the same thing with the other one. I'm just going to say x. Oops. I'm just going to say x of 3.00 seconds. And this time I'm going to say 4 times 3 raised to the third power plus 2 times 3. And then I'm going to say minus 3. And this gives me 111. The 3 cubed would be 3 times 3 is 9 times 3 again is 27. When I multiply that by 4, I get 80 plus 28. That'd be 108. So that's 3 sig figs, only good to the nearest whole number. 2 times 3, that's going to give me 6, and it's good to a little bit beyond the nearest whole number. And the minus 3, that's going to be 2 decimal places beyond the nearest whole number. But since the first one only gave me the nearest whole number, I can only write this as 111.0 with a bar under it meters, because it really is only 3 sig figs. Okay. Oops. So that's the answer for part B. Now for part C, they want to know what is the average velocity over that interval. Well, the average velocity we know is displacement divided by time taken. So V bar is equal to delta X over delta T. And of course, that would be the final position, which would be x of 3.00 seconds minus x of 0.125 seconds divided by, basically you're taking 3 seconds minus 0.125 seconds. So that's 2.7, was it 875, excuse me. And that's actually 1 extra sig fig, so I have to put that in there. So what I'm going to do is say negative, oops, I'm going to say negative 2 point, nope. I'm going to say the answer for the 3 was 111 minus negative 0.2742, which is 111.2742 divided by 2.875, and that's meters over seconds with that extra sig fig. So I'm going to say divided by 2.875. And by the way, none of these digits are significant. So I got 3 on top and 3 on the bottom. That gives me 38.70 meters per second. And again, that's 1 extra sig fig. And I underlined it so we'd know. But if I use that in subsequent calculations, I could use that 0 just by knowing that, and that's, that's why we do it. Anybody have any questions on part C? Pretty straightforward, right? Now, part D, it says, what is the instantaneous velocity and acceleration at 3 seconds? Well, that's where we're going to use another one of our principles that we discovered from our kinematic equations and our introduction to kinematic equations. we know that v is equal to dx over dt, and we know that a is equal to dv over dt. And all we have to do is compute that. So v equals d by dt of 4.00 t cubed plus 2.00 t minus 3.00. Of course, we've all figured out what those units are now. But the main thing is when I take the derivative of 4t cubed, I end up getting 12t squared. And then when I take the derivative of 2t, I just get 2. And when I take the derivative of -3, I get 0. So that's the velocity as a function of time. And then I'd say, okay, velocity at 3.00 seconds is 12 times 9 plus 2. So 12 times 9 is 9108. Yeah, it's 108. And then I add 2 to it, I get 110. And you could follow at check your units, like the units that I said the 3 would have, or the 4 would have, and the units that the 2 would have, and the units that the 3 would have, and all that. And you should see that this still works out to be meters per second. So I did get the instantaneous velocity as 110 meters per second at 3 seconds. Now I can do the acceleration by taking the derivative of that. And since I left it in the functional form, I can still do it. If I had just kept the 110 and not written down the actual function, I wouldn't have anything to take the derivative of because it'd just be a constant. But I do know that a is d by dt of the velocity, and we found the velocity was 12.00 t squared plus 2.00. And now when we take the derivative of that, I get 24.00 t. And then the derivative of 2 is 0. So I just get that. That means a of 3.00 seconds is actually going to be, I really should have written this a little cleaner. So a of 3.00 seconds is going to be 3 times 24, which would be 60, 72. That's 72.0 meters per second every second. Again, I recommend you using that terminology. Even if you write meters per second squared, that's fine. But do take the time to try to read it as meters per second per second. Just because what it means is if this thing started from rest and it had an acceleration of 72 meters per second every second, you know that after 1 second, it would be going 72 meters per second. After 2 seconds, it would be going 144 meters per second, and so on and so forth. That's really the purpose of breaking those units up that way. Anybody have any questions about that? Okay. So that's some pretty straightforward stuff. Notice there's sort of a hierarchy here. You're going from position. If you want to go from position to velocity, you go down. And down starts with d, just like derivative starts with d. So if I take the derivative of the position, I get the velocity. If I take the derivative of the velocity, I go down again, I get the acceleration. And because of the fundamental theorem of calculus, that suggests if you had an acceleration, you could go up to velocity by doing the opposite of a derivative, which is an integral. And then if you had a velocity as a function of time, you could do the opposite of differentiation, which is integration, to get the position as a function of time. But when you think about it that way, you're going to all of a sudden say, oh, well, I completely understand now why integrals without a range of integration have to have a constant of integration. So just keep that in mind. Going down is derivatives, going up is integrals. And when you're doing integrals, you're going to have to use constants of integration or ranges of integration. So any questions before I go on to the next one? All right. So what you might not know is even though I think I mentioned it to you, when I went through the derivation of deriving the kinematic equations, I started with A equals a constant. So I just said A equals a constant, and then I wrote A equals dv dt. I multiplied both sides of that equation by dt, so I got A dt equals dv dt. Then I took the integral of both sides. And I chose to integrate A dt from t equals 0 to t. And I chose to take the integral of dv dt from v equals v0 to v, and specifically v of t. That's how I avoided a constant of integration. And the right-hand side became v of t minus v of 0, while the left-hand side became at. Then I could solve for v of t, and I got v of t is equal to v0 plus at. I set that equal to dx dt and did the same thing, multiplied by dt, took the integral, blah, 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 and that ultimately gave me the x equals 1/2 at squared. So the whole reason I showed you that wasn't to show off my mathematical skill, okay? I'm pretty limited on that. But also the main reason that I did it was so that you'd understand how to treat it if in the event you were given an acceleration that wasn't necessarily a constant. So I have this next problem here for you, and it's one where the acceleration is not a constant. You can tell I expected to possibly take extra time or extra lines on that last one, so I left a blank page. I'll fill that in before I start, but now we're going to see what I mean by doing this for any arbitrary problem. So it says a remote control car is found to have an acceleration a of t equals 0.333 meters per second cubed times t plus 0.100 meters per second squared. So that's the acceleration. You see, it's a function of time. So clearly it cannot be a constant. So clearly we need to be able to use what you learned from me integrating a equals a constant. This time, though, instead of me choosing the ranges of integration, I'm just going to do a integration constant. And then hopefully you'll see between the version where I derived it and the version where I'm doing it now, you'll see a connection. And one of those ways you'll probably like better than the other. But the more important thing is you'll know how to solve the problems, and you'll have some respect for where the integration constant came from. So let's start off. I'm going to make use of the fact that A is equal to, actually, I'm going to make use of the fact that I'm using red. A is equal to dv dt. I'm also going to make use of the fact that v is equal to dx dt. Okay. I've dealt with the units. You should check to make sure those units that I gave, the 0.333 and the 0.100, you should check that they are exactly the units you have to have. I've already done that, but I'm going to say 0.333 t plus 0.100 is equal to dv over dt. Now what I'm going to do is multiply this by dt. Somebody just came in, I think. Yeah, there it is. And I'm going to multiply this side over here by dt. And then I'm going to integrate. Okay. So what I'm going to get is the integral of 0.333t plus 0.100 dt is equal to the integral dv dt. So the integral of the left-hand side would be, because I'm integrating a constant times t, that's going to become t squared, and then I'm going to divide by t. You might also notice that 0.333 is 1/3, so we can save a lot of time by writing 1/3. I'm going to do that. Just remember it's 3 sig figs. So let me write that in here. And I said approximately. That's because we don't know what digits come after the 3. I'm assuming 0, but it could be anything. So we really can't say it's exactly 1/3 because it'd have to be 3 with infinity or an infinite number of decimal places. And the same thing with the 0.1, that have to be with an infinite number of 0 decimal places, but we can use it approximately. So what I'm going to do is, since I integrate 1/3 t to 1/2 of 1/3 t squared, that becomes 1/6. Oops, write it. I did want to write it in purple again. No, I wanted to write it in red. I was right the first time. So that's going to be 1/2 times 1/3 t squared plus 1/10 t plus a constant. Now, the right-hand side is the fundamental theorem of calculus. It basically says, hey, the integral of the derivative is the original function. So I'm just going to say it's v. But because I didn't have a range of integration, I might have another constant of integration that I call C1 there. Now I could bring this back over and say v is equal to 1/6. Notice I just went ahead and multiplied the 2 by the 3. T squared plus 1/10 t. Now I'm going to say, if I pull the plus 0.1, so I could say, for instance, minus C1, I would get plus C minus C1, but that's just another constant. So I'm just going to call it another constant. Let's call it C2. So I'm going to say plus C2. Okay. Now I was given this information right here. It says if the velocity at t equals 0.00 seconds is 3.50 meters per second, what is the car's average acceleration from t equals 0 seconds to t equals 2 seconds? So I've given myself some extra information about this problem by saying what the velocity is when t equals 0. So now I can say v of t equals 0.00 seconds is equal to 3.50 meters per second, but that's also equal to 0 plus 0 plus C2. So from that, we can discern that C2 is equal to 3.50 meters per second. Does that make sense to everyone?
Can you explain again where you got the 1/2 from when you did the integration?
Yes. When you take a derivative, you take the exponent and you bring it out in front, and then you subtract the 1 from the exponent, and that's the new exponent. When you integrate, you do the opposite. You take the exponent and you add 1 to it, and then you divide by whatever you got when you added 1 to that exponent. So the exponent was 1, it became 2, and then I had divide by 2, and division by 2 is the same thing as multiply 1 by 1/2.
Okay, I got you. Yeah, I remember that now.
Yep.
Yeah.
It's really easy to slip into doing integration when you mean differentiation and vice versa. Somebody else.
And after you integrated, you said you plugged in the 0.005,
Mm-hmm.
and that's how you got the 3.5.
I plugged in the 0.00 seconds. In other words, everywhere I
Oh,
had
okay.
the t, I put in 0 seconds. That's why I got a 0, because it's 0 times 1/6 is actually 0 squared times 1/6 plus 1/10 times 0 plus C2. And then, of course, that had to be equal to 3.50. So that's where the C2 became 3.50.
Oh, okay.
Okay. Anybody else? These are good questions. That's the main thing, is that you're following it. What you want to be able to do is on your own, like, open up this problem, maybe change some numbers, maybe not, and just try to do it on your own without watching my work or without looking at your notes and see if you can do it, because this is something that you're definitely going to be tested on. It's one of the fundamental skills that you're supposed to be getting in this class. Okay. Now I can conclude that v of t, oops, I want to go back to red. V of t is now specifically equal to 1/6 t squared plus 1/10 t plus 3.50 We know that unit is meters per second, but I'm going to leave it off for right now. Okay. So now what I'm going to do is say, okay, well, that's my velocity as a function of time, but I also know my velocity as a function of time is equal to the derivative of position with respect to time. So I'm going to say 1/6 t squared plus 1/10 t plus 3.50 is equal to dx dt. And of course, now I'm going to go ahead and multiply by dt on both sides. And then I'm going to integrate both sides as well. So now when I integrate 1/6 t squared, that's going to become 1/18 t cubed, because the exponent is going to go from 2 to 3, and then I got to divide by 1/3, and I already have 1/6 down there, so 1/3 times 1/6 is 1/18. So I'm going to get 1/18 t cubed. Now, the 1/10 t is going to become 1/20 t squared. And the 3.50 is going to become 3.50 t. Okay. So that's the integral on the left-hand side. So I just have to say plus c. And then I say the integral of dx dt with respect to time is just x, but I have to add a constant of integration there too. So I'm going to call this one just plain c. Now I can combine them and say x of t is equal to 1/18 t cubed plus 1/20 t squared plus 3.50 t plus a brand new constant that I'm just going to call C3. Okay. Now up here it says in part A, if its velocity at t equals 0 second is 3.50 meters per second, and its position at t equals 1 second is 0.500 meters, what is the car's average acceleration? So I've got more data. This time I didn't choose to give you a position at t equals 0. I just chose to give you a position at t equals 1, just to show you that you can still do it. So in this case, I'm going to say, now we have 1/18. Let's go back to red. 1/18 times 1.00 cubed plus 1/20 1.00 squared plus 3.50 times 1.00 plus C3. And that's all, since that's velocity as a function of time with the time filled in, that's supposed to be equal to 0.500 meters. So we can see that 1 divided by 18 is 0.0555. So I'm going to say 0.05555. And then, of course, we know 1 divided by 20 is 0.05. So it'd be plus 0.0500 plus 3.50 plus C3. And all this has to be equal to 0.500. So this tells us that C3 must be equal to 0.5555 plus 0.05 plus 3.5 minus 0.5. Oh, actually, yeah, that would be it, but that'd be negative C3. So that's going to give me negative 3.60. And all of these should be good to at least 2 decimal places. So that would be like that. And that should be C3. So now I can say that x of t is actually equal to about 1/18 t cubed plus 1/20 t squared plus 3.50 t minus 3.605. So this is the actual position as a function of time. This is the actual velocity as a function of time. And of course, we already had the position as a function of time, or excuse me, the acceleration as a function of time. So what I want to do in part A is find out what is the car's average acceleration from t equals 0 seconds to 2 seconds. So now they're asking for an average acceleration. Well, we know the definition of average acceleration. So for part A, average acceleration is supposed to be v final minus v initial over delta t. So I've got to compute what the final velocity is. That means the velocity at 2 seconds. So v final equals velocity of 2.00 seconds. And v initial is equal to v of 0.00 seconds, like that. So I can continue on, and I'm going to say, let's copy this. Okay, so I got all that stuff. So now what I'm going to do is say that A average is equal to V of 2 seconds. That's 1/18 times 2.00 seconds cubed plus 1/20 2.00 seconds squared plus 3.50 times 2.00 seconds minus 3.605. That should be so 2 to the third divided by 18 gives me 0.444. And remember, I really only had 3 sig figs, and the unit should come out to be meters per second squared, which we call meters per second. And now I'm going to do 4 over 20, which we can see is 1 over 5. So that's 0.200 meters per second every second. And then plus 7.00 meters per second. And then minus 3.605 meters per second. So we can say 0.444 plus 0.2 plus 7 minus 3.605. And that gives me 4.0394. It does look like 2 sig figs is how many sig figs we're going to have. Our 2 decimal places gives us how many sig figs we're going to have. So that's ultimately that. Oh, that was supposed to be V, by the way. Sorry about that. Oh, wait a second. Did I copy the right one? Yeah, I did copy it. It looks like I wrote an X up there, though. That was... Holy crap. Is that what I used? Ah, man, I used X. I was supposed to be calculating V. Okay, everybody, ignore that for a second. Let's kill this. Notice I copied the velocity. I mean, the actual X position over here, not the velocity equation. So that's where I screwed up. I just took it and didn't pay attention. So VF, we already decided that VF is equal to v of 2.00 seconds. So I've got to go back and plug in my v, which is 1/6 t squared. So 1/6 2.00 squared plus 1/10 t and then plus 3.50. Sorry about that, everyone. Feel free to tell me if you see me screwing up like that. I don't mind. It's not going to offend me and definitely would help me. So if I do 4 divided by 6, that's basically going to be 2/3. So I'm going to get 0.6666, carrying 1 extra decimal place. That's meters per second, not meters per second squared. And then 2/10 would be 0.2. meters per second, and then plus 3.50 meters per second. So I can add all those. I'll say 0.6666 plus 0.2 plus 3.5. That gives me 4.36. With 1 extra sig fig would be another 6. So I'll round that to 7. 4.367 meters per second is the final velocity. The initial velocity is v of 0.00 seconds, which is 1/6 times 0 squared plus 1/10 times 0 plus 3.50, which gives me 3.50 meters per second. So I can finally calculate the average velocity as, or excuse me, the average acceleration as 4.367 meters per second minus 3.50 meters per second divided by 2.00 seconds minus 0.00 seconds. So that gives me 0.866. Actually, I should do that last one. I'm going to call that a 7.867 divided by 2.00, and this is meters per second, and this is second. That gives me 0.433. Notice how the subtraction made me lose a sig fig, and that's meters per second every second. So the average acceleration is 0.433 meters per second every second. Any questions on that one? Sorry about that little screw up in the first part.
Nope.
Now let's look back at the question, make sure I answered everything. It said, what is the car's average acceleration from t equals 0 seconds to t equals 2 seconds? So I just did that. Now they want to know what is the average speed in that interval. Now that's where we actually have to use the x, because the average speed is the distance traveled divided by the time taken. And you really have to watch out for that. For instance, if you have a x as a function of time that goes like this and then comes back or something, then the distance traveled is different from the displacement. So if you're doing average speed, you can just do the total distance. If you're doing the average velocity, which is not what we're looking for, then you just need to know the final displacement. So you have to sort that out sometimes by graphing the function or something like that. So keep that in mind. I did find that x of t was this quantity, so now I'm going to use it this time, only doing so correctly. Okay. So I'm putting it right here, and we're going to do part B. In part B, they're asking for the average velocity. Let me double check that. Average speed, excuse me. What is the average speed in that interval? So the average speed, S, is distance divided by time. Okay. So if I wanted to take and look at something like 1/18 t cubed, I got to look at it between 0 and t. What I would generally do in such a case is throw it in Desmos or quickly plot it or something like that. If I plot this in Desmos, I'm getting ready to do that now. Let's try. So 0.05556 x cubed plus plus 0.05 times t squared plus 3.5 times x minus 3.6055. Okay, so when I look at this graph, I'm seeing it actually have quite a bit of curving, but all that curving happens way beyond x equals 2 or t equals 2. Let me stop for a second and share the screen. Let's stop sharing that screen. And now let's start sharing this other screen. Share screen. So now if you look at this graph, notice it doesn't look crazy. And then going from, I had to use X, of course, but we're using time. So this is 1 second and this is 2 seconds. And you can see that basically the distance traveled is the difference in X's is literally the distance traveled. So at t equals 0 seconds, it was at 0 meters. And then t at 2 seconds, it was at 4 meters. So actually at x equals 0 seconds, it was negative 3.605. I have a pen somewhere around here that I can write that down. And my pen's missing. Oh, there it is. So it looks like this graph says x of 0 is negative 3.6055, right? And then x of 2 is essentially 4. It's getting like 3.99. So x of 2.00 seconds is 4.000 meters. Okay. So really all I have to do to calculate that one, now that I've established that it didn't do anything where it turned around or anything like that. Now you're allowed to use a graphing calculator. Obviously you can't pull out Desmos in class, but you are allowed to have a graphing calculator if you want to do that. You can also just graph it. You know how to find the critical points. The critical points are where it would turn around and stuff like that. So if you don't find the derivative equal to 0 anywhere between the 0 and the 2, then you know you're good, right? If you did find the derivative equal to 0, then you'd have to look at it and say whether that's a maxima or a minima and then see what actually happened. So we went from negative 0.3605 to positive 4. And I just tried to write on my laptop, on my iPad with an actual marking pencil. So that wasn't cool. Everybody got this graph though? All right, let's stop sharing that. Let me go back to my notebook. Classes. Oh crap, class is over and my alarm was turned off. I'm sorry, I ran 9 minutes over, everybody. I'm going to finish this up. Y'all are welcome to go. I'm going to go ahead and finish this up. It'll at least be on the video. So thank you for coming, everyone. and I do appreciate it. And I'm sorry, I thought I had my alarm set to warn me at 6:38, but it didn't happen. So anyways, I'm going to take this and say the distance traveled is actually 4.00 meters minus negative 3.605 meters divided by, and of course the time is 2.00 seconds. So that's 7.605 divided by 2 gives me 3.803 meters per second is the average speed. So that was part B. And so what is the average speed in that interval? And then what's the instantaneous velocity at v equals 2 seconds is what I was supposed to say. Yeah, that's what I said. Good. So for part C, I just do v of 2.00 seconds. Well, we know v is 1/6. Then I'd say 2.00 seconds squared plus 1/10 2.00 seconds plus 3.50, and that gives us 0.667 plus
Is that the 4.36 that you have at the top?
mm,
The final?
at the very top, I had 4.000 minus negative 3.605. Is that what you're talking about for the line on the S bar?
The V final, is that the same as what you're trying to calculate now?
Oh yeah, that's right. I did do that, didn't? Thank you. That's what you checked. Yeah, awesome. Good job. I thought I had calculated it, but I
Yeah.
went on another page. Excellent. So yeah, that should be 4.367 meters per second. Thank you for saving me that trouble. And that's it. So this is, you'll see there's very much problems like this in the practice test. That's what I wanted to make sure I got at least one example for you guys. So we did most of it before the time was up, but I apologize for keeping you guys late. If anybody has any questions, you're welcome to stick around. Do y'all have lab? No, you have lab another night. That's right. So anybody have any questions now? It's basically just office hour time.
No, thank you.
You're welcome. Thank you for coming.
You have a good night. Feel better.
You too, Jennifer. Thank you.
Excuse me, Professor. Is the chapter 2 homework still due tonight on Pearson?
It should not be. I'm definitely changing it.
Okay.
It is. So let me look on there right now. In fact,
Got it.
I'm open. Yeah, let me go change that real quick.
Okay. Well, thank you, Professor. Have a great night.
You too. See you, Joseph.
Yeah, so I had a couple questions about some of the chapter 2 homework.
Okay, go for it.
The first one I had, I wrote down the problem numbers. I don't know if you're able to bring those up or if I need to like bring it up and screen share it.
You can bring it up and screen share it. That'll be fine with me.
All right, let me.
I'll set it up so you can share, but let me fix this grade right quick. I mean this date real quick before I forget. So we had it at 9/11. I'm going to go ahead and leave it till the 15th for chapter 2. Chapter 2 homework and chapter 2 conceptual. All right, I did that. Now on the save thing, I'm going to say stop share. On the share thing, I should say. I'm going to stop share, and then I'm going to allow others to share. So you should be able to share whenever now.
I've never tried. How do I go about doing that?
There should be a button down along the bottom somewhere.
Is this a share?
Yeah, that should be it. And you might have to click like the arrow next to it and it'll give you choices.
Okay. So I did that. Let's see how this works.
It looks like it's doing it. Yep.
Okay, so on this one, starting with, sorry, I had a note written down from basically, okay, I think this is kind of what you just went over, but I wasn't
Exactly.
sure from C to like F. I wasn't sure about any of this, and it wasn't too clear, at least for me, in the book,
Gotcha.
what they were asking or what they meant. Because I
So it
guess,
says,
okay, so it gives at the top up here, this is, the object, the positions given by this.
right.
And then on C, it asks, what is the acceleration as a function of time? And I, for the life of me, could not figure out any of that.
Okay. Scroll up to the top. Let me show you what's going on with that. This actually looks just like the example the textbook gave you in chapter 2.
Mhm.
And they said, I think they said A was 2.10 meters and B was negative 2.80 meters per second or something weird like that. But they actually gave you the correct unit. So what you know is the X is a position. So that has to have units of meters.
Uh-huh.
And that means the whole right-hand side has to have units of meters. So that also means A times time, which has units of seconds, has to be meters. So can you think what A has to be? You got it right, but do you see now why it's got to be meters per second?
Yeah, okay. So I understood A and B.
Okay,
But starting with C, where I guess it was getting into what you were just doing,
gotcha.
is
Ah,
where it completely lost me.
okay. So that's a problem where you're sort of getting a little confused because everything looks like a variable, and
Yeah.
that's perfectly normal. Okay. But when you're taking the derivative of x with respect to t, you're just going to pretend the A is a 4 and the B is a 5, and then change it back to A and B after you're done. So literally, it's okay to write that in and pretend instead of having AT plus BT squared, say you have 4T plus 5T squared, and then just don't combine like terms until after put it back in forms of A and B.
Mhm.
Could you then take the derivative of 4T plus 5T squared?
Well, I also, when it just asked it as a function of time, I didn't realize it was asking you basically to differentiate.
Gotcha.
If I had known that's what it was doing, it would have made more sense. But like, I just thought it was like asking me to kind of like rearrange it and solve for time.
I gotcha. Yeah.
So I was really confused by that. And that's kind of how, uh, let's see. Yeah. So then once it has you set up that, so I understand now that seeing your example where they
Gotcha.
got 2B, obviously, yes, if you differentiate, where'd it go? If
Yeah.
you differentiate that, the AT would go away, the BT would become 2B.
Yeah, the first derivative is going to give you just A,
Oh, yeah, yes, yeah.
and then the second term, taking the first derivative of that would be 2bt. So yeah, it'd be A plus 2bt would be the velocity. And then you take the second derivative,
Oh,
A
okay. So
would
it's the
disappear and
second derivative because position, and then the derivative of position is
velocity.
velocity, and the derivative of velocity is acceleration.
There you go. Exactly.
Okay. So I got that now. Um, okay, so then when it asks for what the velocity is at 2 seconds, you would have to first take the derivative of this. I hate how it's two scroll bars. So
Yeah,
you have
just
to
one
take,
time. Yeah.
yeah, you have to, so first you would find the derivative to get velocity, which would be what you just said, which would be A plus 2BT.
Exactly.
And then since it's asking you at 2 seconds, you would just plug in 2 for the T's
Yep.
and solve it essentially that way, which is where they would have gotten, since it's just A, that wouldn't change, but the 2BT would become 4BT
Or 4B.
or 4B. Yeah.
Exactly.
Okay. And then the same thing essentially for this one,
Yep.
E, and then F.
Of course, by the time you took the second derivatives, there's no time left, so you're just going to get what's left, which is just a 2B.
Mhm. And then,
Okay.
what was it? And all this did was change your uh, exponent. So it's basically just
Exactly.
asking you to, okay. So now that after seeing your examples and realizing that's what they were talking about, I understand this now.
Gotcha.
I
That's
didn't realize they were just throwing in calculus all of a sudden. This was the first question that they had asked anything about calculus, but without mentioning it. So I was very
gotcha.
confused.
Yeah, and that's a big thing to learn is just learn that the derivative of x is velocity, the derivative of velocity is acceleration, and then if you want to go the other way, the integral of acceleration is velocity, and the integral of velocity is position.
Okay. And then let me bring up this other one I had a question about. Okay, so yeah, this is the
Okay.
so
Velocity, what's the velocity versus time graph of a motorcycle whose speed is increasing?
yeah, and eventually, because you get 5 tries, eventually I got it right, but I this is the one I guessed last, and I wasn't sure why because I was thinking it could have been. I didn't think it was A, obviously, because velocity's staying the same.
Exactly. And
Uh,
that the B one looks wrong because it's negative, but remember the negative is not the magnitude, the negative is the direction.
but I also was wondering why wouldn't C be it because it's going from negative to positive, so velocity would be increasing, wouldn't it be?
Yeah,
Oh no, it's decreasing because it's going from a higher speed closer to zero because it's about to
exactly.
change direction.
Exactly. It's going from a higher magnitude to a lower magnitude, but both of them are negative. That's why it looks a little
I
misleading.
got too caught up in thinking it as a number line as opposed to just a
Exactly.
representation. And obviously D can't be it because that is showing you going closer to zero again. So the only one going away from zero is B.
Yep.
Okay. All right. So there's that.
Sometimes it helps if you get a little confused like that. It helps to just assign numbers to the tick marks. And as
Uh-huh.
long as you're sort of consistent with it and it doesn't say not to scale, then you can actually do that and get an idea what it is. And just, use formulas like the average velocity or something like that, and that'll get it for you. Looks like you figured that other one out really good, so that was cool.
Okay. This one.
Air resistance is negligible and an astronaut drops a rock from a cliff and notes that the rock falls about d meters during the first t seconds of its fall. Assuming the rock does not hit the ground first, how far will it fall during the next 4t seconds? Okay. So what they're hinging on there is your understanding of how position and time are related. So when we integrated a equals a constant, which is basically the same kind of problem we're doing here. When I did that to derive your equations, your kinematic equations, I first said A equals a constant, and then I said A is equal to dV/dt. I integrated both sides. That gave me A times T plus V0 is equal to V. So that's your velocity is equal to V0 plus AT. And then I said V of t, which is V0 plus AT, that's the actual velocity. So that's dx dt. And you integrate that one, and you end up getting 1/2 AT squared plus V0t plus x0. So if you drop an object as it is here, the initial velocity is what?
Zero.
0. So the 1/2 AT squared plus V0t plus x0, that V0t is going to disappear.
Uh-huh.
And you can always make the origin so that the x0 disappears. So you see that x goes like 1/2 AT squared. So what
Okay.
happens when you double the time? What happens to the x? Does it double or does it triple? Does it quadruple, nintuple?
And you're talking on the kinematic equation with the 1/2, correct?
Exactly. Ignoring the
So
V0t and the x0 equation, part of the equation.
and so you were saying if you were to double what?
If you doubled the time, what would happen to the x on the other side?
It would well you're squaring time,
Exactly.
so it'd be times itself.
Exactly. So, like, if you just pretended A was 10, because that's really close to 9.8 and it's pretty good,
Mhm.
then 1/2 A would be 5.
Mhm.
And at 1 second, X would be 5 meters.
Mhm.
But at 2 seconds, X would be 20 meters. So,
Okay.
in doubling the time, you went from a distance of 5 meters to a distance of 20 meters, which is 4 times as big, right?
Okay. Yeah.
So what happens if you go to a amount of time 4 times as big? Or let's try 3 times as big first.
It would go up 4 times.
If it was, okay, remember, try 1/2 A is equal to 1/2 times 10. So that'll be 5. And then just write X equals 1/2 AT squared and do it for 1 second, then do it for 2 seconds, then do it for 3 seconds, then do it for 4 seconds and see what you get in each case. I'm trying to let you discover it yourself. I don't want to just give you the answer because it's a much more effective thing when you discover it.
So do 1/2 10 times 1, 1/2 10 times 2, 1/2 10 times 3.
But don't forget the
Squared.
1, the 2, yeah, square. There you go.
Mhm.
So when you did 1/2 10 times 1 squared, you got,
It'd just be 50.
or just 5, right?
Or I'm sorry, 5.
Yeah.
Yeah, because it's half.
So keep that one in mind while you do the one for 2 seconds.
So it'd be 10 times 2 squared. So that would be 24.
Okay, so 20 divided by 5 is what? Okay, so just write 20 divided by 5 is 4 next to that. Now do the one with 3 seconds. What do you get?
45.
45 divided by 5 is?
9.
Yep, which is 3 squared. Just like the other one was 2 squared. So what do you get when you get 4?
80.
80 divided by 5 is?
16.
So you see that when you quadruple something, the distance traveled would be 16 times because that's 4 squared. If you quintupled it, it'd be 25 times, so on and so forth. Does that make sense?
Yeah, so it's basically okay. Yeah, I see what you're saying.
Yeah, so when you have t squared on one side and it's in the numerator and you got x by itself on the other side, that means x is proportional to the square of the time. So when you double the time, you quadruple the distance. When you triple the time, you nine-tuple it. When you double it, I said you quadruple it. When you triple it, you nine-tuple it. When you quadruple it, you 16-tuple it. When you 5 times it, 5-tuple it, you 25 times it, that sort of thing.
Yeah. And see the way it was asking this question, uh, I wasn't thinking to use one of the kinematic equations. I was thinking based off of what it's saying here, like
Right.
if it's going this much in this time, how much would it go? I was just trying to figure out based on this, not trying to use another equation to figure it out.
Yeah, and that's part of figuring out how physics questions are. So don't feel bad about that. It's more just a lack of experience with physics questions and how they tend to word things. So definitely, it's especially if one time get an answer and you think you understood it, make sure you ask me or someone who did get it right and get them to give you as little information as possible, but definitely give you information to help you. And I'll try to do that because I want you to discover the result as much as you can, as opposed to me just giving you an answer. But when you're talking to someone else, they're not necessarily trying that; they're just trying to help you. So you got to be a little careful. But do you have a problem with this one too?
Yeah, I wasn't sure exactly what it's showing or how it's asking.
Okay. So suppose an object initially at rest suddenly experienced an acceleration that was not constant, and instead, so this time it's linearly increasing. And really what it means, linear would mean x equals at plus c, right? Because that's like y equals mx plus b. But in this case, they're just saying x is equal to a times t. So that's directly related. So in principle, when you double time, you're supposed to double distance. When you triple time, you're supposed to triple distance. But if you had an exponent of 2 on there, it would be double time, quadruple distance, triple time, nine-tuple distance. If it had an exponent of 3, then it'd be even bigger because if you double the time, it'd be 8-tuple. And if you triple the time, it'd be 27-tuple. In this case, he said, how would the position of the object relate to time? So we've got the acceleration is proportional to the time. What mathematical operation do we do to get from acceleration to velocity?
From acceleration. So you're going down, so take the derivative of,
The other way. It's the integral in this one.
oh, so going from velocity to acceleration is integral?
No, from velocity to acceleration is derivative, but from acceleration to velocity is integral, and that's where we're going. We've got
Oh,
is proportional to t.
okay. Is that what that means? Is proportional?
Yeah, that little squiggly, or sometimes it looks like a fish without the end of its tail. That usually
Oh,
means proportional.
okay.
Yeah, that's another thing. We just throw that at you and expect you to learn it.
Yeah.
Get up to speed, man. So, do you understand what I'm saying about having to integrate a to get to v? And then you got to integrate v to get to x, and that's what they're asking you about. What happens by the time you get to x?
So starting at A, your exponent, I guess as you go up, your exponent would increase.
So, what's v proportional to?
E would be x squared or
Or
t
t squared.
squared.
Yep. And what about x?
So then x would be t to the third.
Yep. Now you see how they got it, right?
Yeah, I mean when it's spelled out better than
Exactly.
using symbols and asking in a way like none of those seems to ask what they actually want to ask unless you already know what they're talking about.
Exactly. That is somewhat of a problem. That's why you definitely want to ask me questions. These kind of questions you can send to me in a text, and you've got the answer choices right in front of you. So if you send me a picture, I can say, think about what you're going to do and that sort of thing. So feel free to ask me those questions, and I normally, if you text it to me, I respond pretty quickly,
Yeah.
unless I'm right in the middle of class or something.
Well, I had
Um,
a couple of these. I think I had emailed you last week.
no,
Uh,
that's a whole different story. But yeah,
yeah, I emailed you Friday. I
yeah,
think I
I think I
emailed you one
remember
over
getting your
the,
email.
and then I know I had texted you, I think yesterday asking if you could meet yesterday.
Right. Oh
But there
yeah,
was,
that's you were the one that asked about meeting.
yeah,
Gotcha. Yeah.
because I was gonna see if you could help me after class Monday, but then class got canceled Monday. Um, but there's one more I sent you a picture of that I'm gonna have to, I guess, change what I have shared so I can show you that because it's not in the same screen.
Oh, okay.
Uh, or maybe it is. Are you seeing a blurry picture?
I see question 4 at time t equals 0 seconds.
Oh, okay, then that is it.
Okay. So it says at time t equals 0 seconds, a car is traveling along a straight line at a speed of 20 meters per second with constant acceleration. The car travels 56 meters during the time interval between 2 seconds and 4 seconds. What is the acceleration of the car?
I kept getting 8. And then
Okay.
I also got 6, I think. And even when I Googled the answers, they got 8 and 6. And then I
Gotcha.
saw one that did get 2.67, but I couldn't log in to see the steps of how they got it. But I could never get anywhere close to that. And
Gotcha.
that ended up being the correct answer, but I have no idea how they got there.
Okay, so with this one, what you want to think about is your kinematic equations. Uh, there's no different set of kinematic equations for different sets of problems. Pretty much, you have a case where either constant acceleration applies, in which case all the kinematic equations we gave you apply,
Mm-hmm.
or it's not constant acceleration, in which case you have to do the integrals to figure out what the velocity and what the position are. In this case, they said a car is traveling along a straight line at a speed of 20 meters per second with a constant acceleration. So that tells you, oh, I know the initial velocity is 20 meters per second,
Yep.
and I know the acceleration is constant. So I can use the x equals 1/2 at squared
I
plus
did
b
that.
squared t,
And
right?
yeah, and I got 1/2 times well, we're trying to solve for A.
Mm-hmm.
Or yeah, we're trying to solve for A. So it was 1/2. I'm sorry, initial velocity. So it was 20 plus 1/2 times A times, and then the T, I put 2 because it's 2 to 4. So the time would be 2 seconds.
Okay.
So
So the Cortros, I'm trying to work it out over here. So what I'm doing right now is I set 56 meters
Yep, 56 equals.
equals, yep, 1/2 A. Now that's supposed to be car travels during that time and over. So that should be that's supposed to be x of 4.00 seconds minus x of 2.00 seconds. So you don't want to just stick it right on a kinematic equation. Since they gave you a time interval and it didn't start with t equals 0, then you've got to do x of 4 minus x of 2 is
What do
equal to
you
56.
what do you mean by that?
Uh,
X is-
so your x equation is 1/2 at squared plus v0t
uh-huh.
plus x0, but you have to do that one for time 2 at 2 seconds, and then you have to do that again for a time equals 4 seconds, and then subtract the 2-second one from the 4-second one.
Oh, so you can't just do it at a 2-second. I figured I would just count the t as 2 seconds as 0 and t is 4 seconds as 2.
You could in principle, but you'd have to, well, it's just be a problem of whether it pans out. You can in
It
general
doesn't.
always go 0.
It
Yeah.
doesn't. It gives you 8.
Yeah. So that t equals 0.00 seconds that they gave us initially, that's what's making it problematic. So because they gave you that and gave you the 20 at that particular time, you can't reassign the initial velocity to some other time. So I've got 1/2 A times 4 seconds squared plus 20 times 4.00 seconds plus x0 minus, now parentheses after that minus because I'm doing x of 4 minus the entire equation for x of 2. So this is 1/2 A times 2 squared plus, again, it's all in parentheses, plus 20 times 2 plus x0. So when I get all this, I get 16 times 1/2 A minus 4 times 1/2 A. So that's what I get for the t squared terms. And then I get 20 times 4 is 80. So I'll say plus 80 minus 20 times 2 is 40. And then I have x0 minus x0. So those just cancel each other out. And all this is supposed to be equal to 56.0 meters. So what I get is 12 times 1/2 A plus 40 is equal to 56.0. Subtract 40 from both sides. I get, and I'm going to go ahead and multiply the 1/2 times the 6. So times the 12 to give me 6. I'm getting A equals basically 2.333 or 2.666.
Yeah, and that's what.
Yeah, the 2.67, that's the answer.
Yeah, I ended up getting. I got 8, and then I did it a different way, and I think I got 3, but I never did subtract the 2 because I didn't realize you needed to do them differently like that.
Right. Let me here, just in case you don't exactly follow it, I'm going to show you what I wrote down on by sharing my iPad screen with you for a second. It should pop up any second now. So we had 56.0 meters is equal to x of 4.00 seconds minus x of 2.00 seconds. And x of t in general is supposed to be 1/2 A t squared plus v0t plus x0. And we also know v0 is equal to 20 meters per second.
Mm-hmm.
So what I did was 56.0 meters is equal to 1/2 A. Now in this case, I write 4.00 squared plus 20 times 4.00 plus x0. So that's the x4. Now I say minus 1/2 a times 2.00 squared plus 20 times 2.00 plus x0. So you can see that this becomes 1/2 a.
Mhm.
For this term, that becomes 16. And for this term, that becomes 4. And notice it's a minus between them. So I got that for those two terms. Then I got 20 times 4 is 80 for this one. And I got 20 times 2 is 40 for this one. And there's a minus between them. And then for this one, I get plus x0, but for this one, I get minus x0. Okay, so you can see the x0 and the minus x0 cancel out. We get 56.0 meters is equal to 12, because 16 minus 4 is 12, times 1/2 a plus 40. So I can subtract 40 from both sides. That gives me 16.0 meters equals 6 times a. Like that. Make sense?
Yeah, and see, I got close to that, but I didn't do the other half basically. So they didn't subtract, which gave me a higher number of 8.
Yeah. They and like I said, that's very typical. That's the one disadvantage, but us teachers sort of like it. The fact that Chegg and various other websites have errors in there, because they pay people very well. They'll claim they pay them a lot of money. They don't pay them much money, because I've been doing it for 20 some years, writing textbooks and solution manuals, and they tell me they're paying me $160 an hour. But I work really hard to make sure I get all of them right, and it works out to more like 15, $20 an hour.
Mhm.
So if you're finding people that really think they're making that much money, they're probably making a lot of mistakes.
Yeah. I had also a question for the extra credit question. This one, I think.
Ah, yes.
Yeah,
I
I was
remember you
confused.
emailing me about that one.
Yeah, I was confused about the B.
The pounds per inch squared foot.
Yeah.
Yeah, so what you have to do is you got to make sure it's in a unit like centimeters cubed or meters cubed or something like that. And then what you do is you say centimeter times a centimeter times a centimeter, and you take one of those centimeters or two of those centimeters and convert them to inches. And then you take the third centimeter and convert it to feet. That's how that works.
Huh. Is that a real measurement?
It is. It's kind of weird. It's something I learned when I took scuba diving in college, because they give you these neat little figures, like the density of water is 64.0 pounds per square inch per foot. And for freshwater, it's 62.4 pounds per square inch per foot.
Oh, so it's per foot essentially. So it's PSI per foot.
Exactly. So it's
That
talking
it
about
when you
how
say
much
it that
pressure.
yeah, when you say it that way, it makes a lot more sense. When you read it as pounds inch squared feet,
Yeah, exactly.
I was very confused by that.
We use a lot of weird stuff like that. I mean, scuba diving was one thing, but like in engineering, when I used to do land development and wastewater and that kind of stuff, we use something called the inch acre, and
Huh.
that's literally an inch multiplied by an acre.
Okay.
The reason being is when you put down impermeable, surfaces like concrete and asphalt,
Uh-huh.
you've got to account for all the water that fell on your impermeable surface, and that's not allowed to be shipped over to your neighbors. So you've got to build these ponds. That's why you see ponds all around malls and shopping
Yeah, the
centers.
retention ponds.
Yeah, the wastewater retention ponds are for that. And the best unit is, hey, if I know the facility's 20 acres of concrete and I get a 4-inch storm, then that's 4 times 20 is 80 inches times acres, or 80 inch acres. So it's a really good unit of volume to use.
Huh.
But
What
yeah, they
is-
do a lot of weird stuff like that. So just keep that in mind. And a lot of times it can be the difference between you knowing what to do and you not knowing what to do just because you know how the units work.
Interesting.
Is Tracy, are you still here? I don't think she's here. She's still listed as here, but I think it might be that she logged out and her phone never logged out. Just want to make sure I won't ignore her. So does that help you? You think you know where to go now with that?
Yeah, I think that's all I got.
And if I'm remembering correctly, I think I even gave you the answer because I seem to recall it being like 64 pounds per square inch per foot. And then 62.4 pounds per square inch per foot was the one for, like I said, for freshwater. We use 1.025 grams per cubic centimeter for saltwater, whereas we use 1.00 grams per cubic centimeter for freshwater.
Yeah, I remember using that in the other physics class I took, but uh, it was a trig-based physics class, so it didn't count towards anything.
Yeah, it's really good for you. God, I wish everybody that took calculus-based physics had the algebra trig-based course first. It'd be so much easier for them.
Well, it would have been if it wasn't like a year and a half, 2 years ago.
Yeah,
So
everything
I
changes
remember
when you get away.
just enough for it to be confusing. I, I I usually keep all my notes just for situations like this. So when I do go to higher maths, then I can go back. But apparently I didn't keep the physics, the first part of the physics. I only kept the pressure, liquid, density, all that
Oh,
part of it,
gotcha.
because that was like the second half of the class. I didn't keep the first half, and I found like one of my formula sheets, but even those look a little different. We didn't use X for initial. I think we used S,
Yeah.
which made
That
these
yeah,
formulas look
I know what
different.
textbook that was too. There was a guy that wrote a textbook. Damn, I can't remember his name now, but yeah, he wrote one where he used S instead of X. I imagine y'all were using that same textbook. It wasn't Tipler. I can't remember the guy's name now.
I don't
But
know. It was all printed out for us. I think it was actually created by. It's in a. I go to. I'm at an apprentice school,
oh, okay.
so
Oh, that's cool.
yeah, it's a Newport News shipyard.
Nice.
So that we. I think they do their own. So I don't know if they use another textbook, but it doesn't reference anybody else. So it looks like it's almost stolen, like not stolen, but they use material from different places and put together their own.
Yeah, it's strictly speaking, it's probably not legal, but it's okay. I mean,
I mean, I'm assuming that's what they do. I don't know if
yeah.
that's
And it
actually
might
what
be
they
a
do.
textbook that's out of print, in which case you'd be hard pressed to find someone to press charges against you. But
Yeah, I have no idea. But yeah, since in the shipyard, we don't anything we do isn't there. We don't use calculus. We use all trig stuff.
yeah.
So all the classes they taught us were trig based.
And to be honest with you, I mean, if unless you want to be an engineer or a scientist, you can do just about everything you need to do without the calculus. But like I said, if you need to go to more serious stuff, sometimes you're just gonna have to suck it up and learn calculus. But you'll see, it'll come back to you. Just take you a little while.
Yeah, and that's what
Is
I'm
there
doing
anything else you
now
need doing?
is going for engineering.
Yeah.
I'm actually working with crane engineers right now, uh, in my current position.
Oh, that's cool. At the shipyard.
Yeah, I was able to talk my way into them letting me spend a part of my apprenticeship working with the crane engineers instead of like the normal